Thank you. So welcome back. I hope you enjoy your lunch. Thank you again to Dunsky and Navius for sponsoring the meals. So this year we're trying something new. We have almost a dozen of great posters out there. We wanted to give them the chance to present their research and titles. And we asked them, and they're up to the challenge, to take 2 minutes to try to explain to you what their project is about and convince you to vote for them, basically. So it's going to be fun, but let's try this. You can, of course, cast your vote using the Slido tools. I'm going to start by presenting the 5 first one, and then we'll move on to the 5 other one. So I'll invite Trevor Barnes from SFU to break the ice, so with 2 minutes presentation. Let's give him a round of applause, of course.
Beautiful. Thank you, everyone. Hi, I'm Trevor Barnes from Simon Fraser University in Vancouver, and I'm here to present the work of pipes who say sector coupled. This is a project I've been working on with another PhD student out of Stanford the past year or so, and it is a full energy system optimization model of the USA, and it is built on the PIPESA framework. So PIPESA can be used for optimization studies of both the power system and the energy system. So this project extends the power system capabilities of Pipes USA to a full energy system. What that means is I include the residential, commercial, industrial, and transport sectors. Each of these sectors have their own demand profiles up to hourly resolution and different fuels. For example, residential and commercial have both electricity, space heating, water heating, cooling demands. Transportation will have demand by node, or demand by mode, sorry. So light duty vehicles, heavy duty, medium duty, and there's electrical load profiles as well as fossil fuel profiles. Pepsi USA sector is a fully open source, open data model. So what that means is it's available in GitHub. Anybody here can go and download and run the model. We use established databases from organizations like NREL and EIA and EPRI to generate all this data. And what that means is going forward, when they update their data, Pipes USA automatically grabs these updates and updates with them. Moreover, we pull in policy constraints from organizations like NREL, so RPS standards and whatnot. From their model, we can directly ingest them into PIPESA for our studies. Finally, PIPESA USA is very user configurable. So what this means, if you want to turn on and off different sectors, if you want to allow different emission limits, if you want to use weather from a certain year, that's all fully user configurable, and there's a lot of flexibility in the types of research questions you can use for it. And with that, I will let it go. Thank you.
Very well done. Thank you, Trevor. Next is Barbar Moawad from Deloitte.
Thank you, everyone. I'm Barbar Moawad. I'm from Deloitte, and I'm the product strategy leader of Electrified Grid, which we're going to be talking about and which you'll see on the poster. So many of us here today have done tremendous work as it relates to modeling the energy transition and in helping reduce uncertainty in navigating it, especially for decision makers across Canada and abroad. And now as the rubber hits the road on the energy transition, what we're seeing and what we're hearing from our clients and what we've heard from Julia as well is that there is a gap, and the gap is related to the distribution infrastructure. We're not doing enough to model the impacts of the energy transition on the distribution infrastructure. And that was the topic of our previous session here. So at Deloitte, we found ourselves to be well positioned to actually fill that gap. And we've developed an approach to really bridge that gap, essentially. And the way we do this is by integrating energy economy modeling with physical infrastructure modeling, by taking a multi-step process that we're happy to walk you through by our poster. But most importantly, it helps us answer questions like how will loads evolve in specific neighborhoods, and how will those loads create congestion on secondary cables, distribution transformers, primary cables, feeders, and how much they will cost to upgrade, and also what is the value of non-wire solutions and how can we prioritize grid modernization rollouts to make the most bang out of our buck, basically. So yeah, we invite you to join us and at our poster, and thank you very much.
Wonderful. Next is Adrien Prigent from Enercan.
Bonjour à tous. Voilà, je suis Adrien Prigent de Enercan. J'ai fait ce projet avec mon équipe du centre de recherche 4M Énergie Varennes. Donc en fait, il présente l'impact de rendre une demande industrielle flexible dans un modèle d'expansion, de planification d'expansion de capacité. Donc il va s'agir de modéliser la capacité de l'usine à ajuster sa consommation électrique selon les besoins du réseau et les variables économiques. Donc notre cas d'étude ici, c'est une usine de pâte et papier en Nouvelle-Écosse. Donc on a réalisé 3 modèles. Un premier modèle avec 3 modèles réalisés avec Pipesa, un logiciel d'optimisation que nombreux connaissent. Le premier modèle est fait avec une demande statique. Le deuxième avec une demande où on a modélisé la demande avec des options de lien pour modéliser les différents états d'opération de l'usine. Et enfin, on a simplifié ce comportement, donc on l'a linéarisé pour obtenir un troisième modèle plus simple et moins lourd à rouler. Donc de cela, en fait, les résultats ont démontré une baisse. Donc on a réalisé une planification de l'expansion de capacité pour satisfaire les besoins électriques en 2050. Et de cela, on a obtenu une baisse d'investissement en infrastructures de transport et de production. Donc ça a permis de déduire que pour ne pas prendre en compte cette flexibilité dans nos modèles de planification peut nous amener à surestimer les besoins d'investissement en infrastructure. Et donc le faire favoriserait des mix énergétiques plus économiques et avec une meilleure adéquation des ressources. Voilà, je vous remercie et j'attends vos questions plus tard à la session poster. Merci.
Merci, Adrien. Next is Pablo Riva de Nera from University of Waterloo.
Thank you very much. Hello, everyone. There are many initiatives around the world to promote the use of microgrids to incentivize the use of electricity and the use of renewable energy, and also the electrification of heating and transportation systems. For example, in the case of Canada, we're seeing that there's an increase or a significant increase in the use of electricity for space heating. And also we are seeing that airports are investing heavily. For example, we're seeing that over 14 billion has been invested in infrastructure and renewable energy sources and the electrification of ground transportation and electric planes. Our poster presents the modeling and optimal operation of a hangar thermoelectric microgrid being deployed at the Waterloo Wellington Flight Center that uses electric planes for pilot training. And our model considers thermal comfort inside different rooms, different spaces inside the hangar building, and also the independent dispatch of heat pumps for temperature control. We're also considering in our modeling the uncertainties and aspects related to battery degradation. Finally, we have tested the performance of the models that we have developed under severe weather conditions, considering the hottest day in summer and the coldest day in winter in the region of Waterloo, using real data for a period of 14 years. We also conducted a yearly evaluation to demonstrate the benefit of the proposed approach in terms of reducing cost and carbon emissions as well. My name is Pablo Verdugo. You're welcome to see our poster in the next room. Thank you very much.
Wonderful. Great pace, guys. So we continue with Luis Lopez from Carleton University.
Hey, hello, everyone. I've been challenged to explain my poster in 2 minutes or less. While I was thinking how about to start my presentation, I realized that making a joke maybe be a good way to do it. So why did the power Greek take yoga classes? And that's because he needs to improve his flexibility. I didn't say it was a good one, but So in this poster, we are talking about flexibility as the ability of the grid that can adapt to different changes in the power demand and the power generation. So basically, we developed a model, an optimization model, to capture all the flexibility coming from the new distributed energy resources and passing that information to the transmission level. So in this optimization problem, we basically modified the objective function to capture that flexibility. The thing is, like, there are very few models right now that can harness really well that kind of flexible operation that we can do it. So if you are curious about how flexibility can shape a sustainable future, and maybe you want to know more back jokes, so my poster is the place to be. Thank you.
Wonderful. Let's continue with Hamad Mohseni Manesh from CanMet Energy.
Good afternoon, everyone. My name is Ahmad Mohseni Manesh, and I'm research scientist at CanMet Energy, Ottawa. EV and renewable energy technology are essential for sustainable development, but the charging infrastructure for large-scale community remain underdeveloped. Our main focus on this project was to develop optimized charging strategy and evaluate energy supply and demand. Using a data set of over 1,000 EVs load model with a machine learning approach alongside energy consumption data from 500 houses model in trans, we propose energy integration solution using Homer grid to establish enhance efficiency and sustainability. We found PV system could cut 35% of the annual energy charging demand. Overnight and workplace charging strategy reduce the power value, peak to average ratio, and also cost and energy cost by 50%, showcasing the feasibility for future application. This finding offer practical solution for facilitating EV adoption and fostering greener transportation system. Thank you.
Thank you. Just be sure to start the clock. Thanks. Next one is, well, Nicolas Leggy is not here from Dalhousie University, but I invite you to visit his poster at booth number 7. Then we move on to Xiao Q from University of Waterloo.
Good afternoon, everyone. I am Xiaoyu Wu from University of Waterloo. Canadian energy sector is responsible for 30% of our greenhouse gas emissions. But in the meantime, the sector is also contributing 10% of our GDP and 20% of our export values. So how can we maintain and keep the output of our energy sector while reducing the greenhouse emissions? Some people propose to use low carbon electricity of Canada to produce hydrogen. That's because hydrogen can be utilized to decarbonize different sectors like steelmaking, like heavy duty transportation. And there's also new customers in Europe, in Asia, that are interested in our low carbon hydrogen. That's why in my research group, we study hydrogen energy systems and economy, especially focusing on low carbon ammonia and understand how this ammonia can be utilized to decarbonize different sectors. We are interested in this following questions. So how can we produce ammonia using our abundant offshore wind resources? And how can we use ammonia to integrate different sectors to decarbonize our agriculture, domestic energy use, as well as energy exports? And how does it cost to reduce 1 ton of carbon emissions by using this new ammonia energy pathways? So if you're interested in these questions, please come to my poster. And again, this is Xiaoyu Wu from the University of Waterloo. Thank you so much.
Awesome. Moving on with Leonard Olian from University of Calgary.
Thank you. And first, wow, what an amazing set of projects I've seen here today. I'm actually feeling a little intimidated. But anyway, my name is Leonard Oline. I'm a PhD student in mathematics at the University of Calgary. This is a project that I've done with Professor Sarah Hastings-Simon, who's in Earth Environment, Energy, Environment, and Earth, also at the University of Calgary. And in this project, we look at the opposite side of the energy transition, which is contraction in the fossil fuels industry. Specifically, we're looking at gas stations. Right now, if you drive a gasoline car, you always think that there's a gas station between where I am and where I want to go. You don't really worry about it. As EVs start to take over, those gas stations are going to start to disappear. You're going to have to go a little bit farther out of your way to refuel your car. And the question is, so will that lack of convenience actually contribute to the acceleration of the adoption of EVs if it's not so easy to fuel up your car? What we found, we've done an analysis within cities, trip behavior within cities in Alberta, just single occupancy vehicles for now. And the answer is we have a lot of gas stations. You can get rid of like 75 to 80% of the gas stations before there's a real material change in driver behavior. So we really don't think that will accelerate EVs. We'll have to have a lot of EVs before we get to that level. But it does bring up some policy questions about will we need either government support to maintain the remaining gas stations, or will we need to implement market power mitigation measures to make sure that those remaining gas stations aren't gouging the few people that are dependent on them. And we think that the results of this could also be useful in extending other energy modeling work in terms of the needs for gasoline and where it would show up. Thank you very much.
And last but not least, David Elder from University of Toronto.
Hey, I'm Davey Elder. I'm from the University of Toronto, working on the Canadian Open Energy Model. So we saw with our discussion earlier today that a lot of these national plans to reach net zero emissions are highly dependent on the emergence of these new energy technologies. But there's a lot of uncertainty around what these technologies are going to cost and how they will perform at scale. So it's sort of an open question of how do we assess these emerging technologies when we really don't know what they're going to look like in the future. And I think the way we do that is we do the work, we do the analysis, we collect evidence, and we tell a story. And I think what I'm proposing with my work here is maybe a new chapter in that story, where instead of trying to project the best estimate of costs or performance into the future and asking our models to tell us how much of this technology we should build, instead, we force the model to build some of this technology at zero cost, and we see how that reduces the costs of the system. Because if we can add a technology to the model and see how it reduces costs, we can see that as being the system value being provided by the technology, the value the technology is providing to the system. And so then we can assess the system value of a technology over a wide range of performance parameters, sort of sweep the parameter space, and try to generate insights about things like what thresholds of performance do we need to reach? How can we maximize the value of a technology in our deployment or in our operations? And we can do other things, like we can disaggregate the value of this technology by splitting it out by where costs were reduced elsewhere in the system. We can see why value is being generated, and that can kind of lead our investigation into more generalizable insights that aren't hugely dependent on the exact assumptions we've made going into our model. And so we think we can use this to get a pretty good idea of the role of emerging energy technologies without knowing exactly what they're going to look like in the future. Thank you. Vote 10.
Wonderful. Let's give them a big round of applause and good luck, guys.